Welcome back to this second lecture in this series on concurrency, state models, and patterns. Today we're going to be looking at concurrency in Java and also how to model concurrency with finite state processes. The outline for today is first we'll have a look at how threads are created in Java, and then, as we saw last week, concurrency in programming language consists of specifying how to create concurrent processes or threads, and second of all, how to synchronize and communicate between them. So we'll see then how synchronization is done in Java. In the second part of the lecture, we're going to see how we can model concurrency using finite state processes, and we'll start with some very easy examples. As a starting point, recall that the words thread and process are often used kind of interchangeably in the context of concurrency, whereas in the world of programming languages and operating systems, there is a subtle difference between them. So threads and processes are both concurrent entities. When we distinguish them, however, in the context of operating systems and programming language implementations, we usually mean that a process has its own address space, its own memory, and it's a more heavyweight entity. So it's something that's big. Whereas a thread is something that tends to be very lightweight, a lightweight process. So it doesn't have its own address space, it doesn't have its own control of the CPU. It's something that's lightweight that may exist within an operating system process. This can be a little bit confusing because when we talk about finite state processes, we're using the formalism of finite state processes to model things like threads. So sometimes the use of the terms can be a little bit confusing. So whenever you hear the word process, you have to think a little bit, are we talking about operating system processes or the formal notion of processes? Usually it'll be pretty clear which we mean, however. Think, however, that a process in the operating system world means like when you're running on a computer, every time you run an application, a word processor, a game, any kind of tool, Excel, whatever, that's usually running inside an operating system process. It has its own memory and it can communicate with other processes either through files or through sockets. It's something that's heavyweight, and the concurrency there is managed by the operating system itself. When we look at the world of Java, however, Java is running inside a virtual machine. That virtual machine is running inside an operating system process that has its own address space. Within that process, the Java virtual machine is simulating lots and lots of threads. So these are lightweight things. They don't have their own address space. They're sharing the address space of the Java virtual machine. And these guys can talk to each other more or less directly, as we'll say, usually through some kind of shared memory, which means other objects that these threads know about. And we'll see how that works in more detail. So process and thread are more or less interchangeable concepts, but when we get to the nitty-gritty in terms of implementation, usually there's a subtle distinction in how these terms are used. Later, however, today we'll see that the world of finite state processes can be used to model either threads or processes in the operating or programming language world. Diving into Java, when we want to create threads, that is, usually when we're writing a Java program, typically we're writing a sequential program that has a single thread of control. But if we want to define multiple threads, we can do that. There's a class in the system which is called java.lang.thread. And one way of creating a new thread is to subclass that thread. So here's an example. There's a class called competitor, and it extends Java lang thread. It has a name, and it has a run method. The run method is very important. So anytime you want to create multiple threads in a Java program, you will need to have classes with a run method. Now there are two situations. One is the one that we're seeing here, where we subclass thread. So we define a new class that inherits from thread or one of its subclasses, and we override run to do something interesting. So in this particular case, we're going to have a competitor in a race that's going to run a 5-kilometer race, as we see here, and it's just going to keep printing some stuff out. And in the race, it periodically sleeps for some length of time and then continues running. And when it's done, at the end, it prints out done. The other way of creating a thread is to create a class which implements the interface runnable. So you're more or less doing the same thing. You're creating a class that implements the method run. However, instead of inheriting from thread and overriding and re-implementing run, what you do is you simply define an arbitrary class that implements runnable, and you implement the run method. In the first case, in order to create your thread, we'll just create a new instance of your class. In that case, it was an instance of the class competitor. In this particular case, you will create a new instance of the class thread and pass in as an argument an instance of your class, which is runnable. So in both cases, you're instantiating thread or a subclass, but in the second case, the actual run method doesn't belong to the subclass of thread, but to an object that you pass in, a runnable object. This is very convenient because in the second case, you're not tied at all to the thread hierarchy. So here, for example, I have the class MT useful stuff, and it extends some other class that's in the system called useful stuff. So in this particular case, if I don't want to inherit from thread, but from something else that's useful to me, I don't have to. I simply ensure that I implement the runnable interface, that is, I implement the run method, which returns void, and pass it into a new thread. So these are the two ways of creating a thread. Now, to instantiate a thread, there are actually 4 different interfaces. You can, but they're essentially 2 by 2. So you can either create a new instance of thread or its subclass without any parameters. That's the default constructor. Or you can give that thread a name, which is useful for debugging processes. And then the same thing is true when you create a thread passing in the runnable. You can just pass in the runnable by itself, or you can pass in the runnable and a name for the string. So there are 2 ways of instantiating threads: subclassing threads or passing in a runnable. And you also have the option passing or not a name for the thread. So 2 by 2 gives you 4 ways. That's it. Now, of course, you will wonder, well, how do I actually start this thread? Likely I'll want to call the run method, right? No. Here's a very important thing to watch out for. So here's an example of a clock class. So this clock extends a canvas, so it has a place to show stuff, and it implements runnable. In its constructor, we call super, which is always a good idea. And we check our instance variable clock thread, which is going to be initially null. And if it is null, we're going to create a new thread. So we'll create the thread passing ourself, because we're runnable, to a new thread with the name clock. And now the magic is that we see here, we call clockthread.start. So that's what we see right here. So notice we do not call clockthread.run. Clockthread.run would simply run that method in the current thread. What we want to do is we want to tell the Java virtual machine, hey, there's a thread here. I would like you to start this thread as a new thread, and be aware of it and start scheduling it and let it run in parallel with me. What's me? Well, that's whatever thread is executing the constructor to the clock. So whichever thread that is, at that point, a new thread, the clock thread, will be started. Now in this example, what we do in the run method is simply update the canvas in a loop while the thread is not null. And when the thread is null, then we'll simply stop doing things interesting. So while the current thread here, is equal to our clock thread, then we'll repend. And that means that we're going to update the display of the clock. We'll sleep for 1 second and we'll loop around. So that means the clock is going to be updated once a second. If at some point we actually want to stop this guy, we will call the stop thread method. The stop method will set the clock thread to be null, which will cause us to exit from this loop. So this is the way of actually stopping that thread by sending it a simple piece of information. Notice that there aren't any difficult synchronization issues here, because the only update that's coming from the outside is setting the clock thread to be null. Let's have a quick look in IntelliJ what this clock class looks like in some more detail. Here we see our clock extends J component in this case, and it implements runnable. It has its clock thread. It has some other bits of information which are useful for displaying the canvas. We have our main method, and we create here our new clock. Here's our constructor. At this point, the new thread is created. So by calling the main program within the main thread, at this point here, a new thread will be created and started. At some point, if we close the window, we want to make sure that the thread will be properly terminated. So when we're closing the window, we'll ask the clock to stop its thread. The stop thread method will be called, set the clock thread variable to be null, and then we'll exit out of this run method. Notice the run method is simply looping around to check whether the current thread is equal to the clock thread. If this variable has been set to null, that means that we should exit and stop. So now if we run this guy, we see in a great big window the current time running. This is being updated once every 1,000 milliseconds, once a second. And if we quit this guy, the clock, not only will the window be closed, but we'll cleanly exit, and we'll see that the process is finished with exit code 0. Now let's have a little bit of a closer look at what's actually happening within Java. What happens when we create a thread? So a thread is just an object. There's a class called thread, and we can create subclasses of it with the run method, or we can pass in an object that has the run method. Anyway, the thread is just an object, and it knows that there's a run method that can be executed somewhere else. Other than that, there's nothing magical about threads. However, the start method is kind of magical, because when we call the start method of a thread, that thread object will tell the Java virtual machine, hey, we're special now, schedule us as a thread in the Java virtual machine. Make us something which is going to execute in parallel. So now there's a whole bunch of these threads in the Java virtual machine, and we can view their execution state as follows, as essentially a state machine with 4 possible states. Here we are initially. This is when the thread is created, and there's nothing special about it. When we execute the start method, on the other hand, at that point the thread becomes runnable. And essentially the Java virtual machine will take this guy and schedule it. So there'll be a queue of possible threads which are going to be executed in according to various priorities in the turns. A thread at any point could call a yield method. Yield, all it says, hey, Java Virtual Machine, if you want to give somebody else a chance, I'm willing to give up the processor for a moment here. So it stays runnable. So it just moves to the back of the queue and some other thread will run. In actual practice, we won't be using the yield method very much, but in some cases it may be useful. Much more interesting is how does the process go to a not runnable state and back again, and finally, how do we get to exit? The last one is really easy. When the run method is over, then we exit and the thread just becomes a dead object, which will eventually be garbage collected when there are no more references to it. More interesting, however, is this transition between run to not runnable and back again. So when does a runnable object become not runnable? The first one that we saw is by calling sleep. So when the clock says, hey, sleep for a second, 1,000 milliseconds, that thread becomes unscheduled and goes into the not runnable queue. However, the JVM knows that a timer should be set, and when that time passes, that thread will be woken up, the time has elapsed, and the thread becomes runnable again. So that's what happened with the clock. There are two more very important ways that a thread can become not runnable, and we'll see these eventually. The most important of these is wait, and we'll look at that in a moment. By calling wait, a thread says, hey, according to my logic, I cannot make any advance until something else happens in the system. Please wake me up when somebody notifies me. And we'll see there's a notify and a notify all, and we'll see how they're used. Finally, if a thread is reading from something, so I/O, input, output, and it's reading, for example, from a file or a buffer or a socket or port or anything, some kind of stream, and there's nothing for it to read, that is, it has to wait until there's something there, then that thread becomes unscheduled and it's blocked on I/O. When that I/O can proceed, then the JVM wakes that thread up and makes it runnable again. So that's the complete story of the possible states that a thread may be in and how it can transition between them. So, to start a thread, you don't call the run method, you call start. So thread's run method should never be called directly. That's a typical error that is easy to make when you start programming with Java concurrency, but instead when you call the start method. So here, for example, if you recall our competitors are running races. Here we create two instances of a competitor. The competitor is a subclass of thread. So we create one competitor which is called tortoise and the other which is called hare. And at this point here, we create the new competitor and here we start it. So at this point, that thread object which has been created gets scheduled and it can start running as soon as it gets a chance. We create the other guy and we start him. Notice we could do this in separate steps. So we could have independently created the two competitors, tortoise and hare, and then at a later point in time started their threads. It's completely open to us how we wish to do that. Now when we run them, there's no synchronization between these. They're simply running their races and waiting and sleeping in between, as you might recall if you browse back at the code we saw earlier. And we'll see that the races look pretty similar each time. However, there's a bit of interleaving. So in one race, the tortoise started first, and then the hare went again, and then the tortoise and the tortoise again. And in another race, they're interleaving a little bit better. So notice that the output lines are being interleaved in various ways, so we're getting some non-deterministic results. Well, this is good because this is exactly what we're simulating in an actual race. In an actual race, we would expect the tortoise and the hare not to be running, not to have the same outcome every time they race with each other. So there's no guaranteed ordering of the threads by the JVM. One question, however, that we'll leave for the discussion time is why the output from the different threads never gets garbled. So how come we never see something that looks like this? 0 ha, 0 torto reise. Have a think about that and see what it is in our program that prevents this kind of conflict. Now, so far, all we've done is we've seen how to create threads and to run them. There's no real synchronization between them, or not any that we paid any particular attention to. We'll now have a look and see how synchronization is managed in Java using wait and notify. And we'll see in the coming weeks that there are a lot of subtle issues here in making sure that we don't have any problems with our synchronization. However, the basic principle is fairly clear. So if you don't have any synchronization, you may have an arbitrary number of threads running at any time within the methods of an object. So I have a single object that's not synchronized. Multiple threads can come in it. They can be this object can be shared, and all of these threads can execute arbitrary methods on the object. If that object has no state, that's not a problem, but most objects have some state. So now we have a serious issue. There's a class invariant. The class invariant, if you recall from your basics of object-oriented programming, the class invariant states which the legal states of an object may be. So what are the valid states? And all the public methods assume that the class invariant should hold. That is, that the object is in a clean state when you start executing. If, however, you're executing a method and some other object comes in, so that means that while you're executing the method, the object may temporarily be in an unclean state. If at that point some other thread comes in and starts executing, it assumes the invariant, but the invariant may not be true. At that point, you cannot guarantee anything, and the whole program may fall apart. So instead, there's a fundamental concept of a critical section. The critical section is a concept in concurrent programming which says, in this block of code, we want to make sure that any thread that comes in here has exclusive access to the state of the object or some subset of its state. So you lock access to the object while it's running. So a critical section, it's a piece of code that accesses a shared resource that must not be concurrently accessed by multiple threads. So a classical way of doing this in low-level programming is with the use of locks. So we saw last week there are notions of semaphores and locks, and you can basically say, okay, here's a critical section in my code. I want to make sure that this critical section is protected. So what I'm going to do is I'm going to put a lock here, and I'm going to release that lock here. Let's see, do we have a green color? Sure. So there's a lock here, and the lock is released, and in this period in between, we have the critical section. So as a consequence, any object that comes in between will be waiting until the lock is released on the critical section. So that's a fairly low-level way of thinking about critical sections, but this is essentially what Java offers, and we'll see how it does it. So in Java, we have a higher-level concept, which is the notion of a synchronized block. So the synchronized block says, okay, we're going to lock this critical section from here to here. And the object that we'll use as a lock is this resource. So that means in this critical section, if anybody wants to access this object called a resource, then they have to hit this boundary first. So we will lock the resource, and when we're done, we'll unlock it, and then somebody else comes in. So if I have one thread coming in here, thread A, it runs through, that's fine. If this thread is at this particular point here, then if another object comes through, then it will block. And only when this guy exits, then the lock is released and the next thread can come through. So that means that at no point in time are both threads in the critical section at the same time. So that's the basic idea. Java offers a more high-level concept, which is that of synchronized methods. The idea here is that most of the time the resource that we want to protect, for which we want the critical section, is the object itself. It's not some external resource, some shared thing. We want to create a monitor. So the monitor means that every object is or can be a monitor, or rather every object is potentially a monitor. So as a consequence, in the synchronized block, you can pass any object in. But as a more high-level concept, you can simply say, I have a method, for example, the method println, and it's synchronized. That means any client coming in and trying to execute the println method will be blocked as long as there's some other object, which is some other thread, which is already executing the println method for the same instance, for the same object. Notice if we have multiple print streams, these are independent of each other. We can freely execute their println methods in parallel. But if we have a particular print stream, for example, the standard output stream, system.out, then we want to make sure that system.out is synchronized with its print lines. Since that's extremely common, as a result, what Java offers is the synchronized keyword as a high-level way of synchronizing an entire method, but it's completely equivalent to saying inside the body of println synchronized this for the entire body of the method. So far, so good. We've seen how synchronization works. How do we interrupt it? So this is where the notion of the monitor that we briefly saw last week comes in. So last week we saw the classical ways of managing synchronization with a monitor are with the keywords wait and signal. In the case of Java, we have not wait and signal, but wait and notify, or wait and notify all. Notify all is a variant of notify, which is usually more useful. Furthermore, these are not keywords, they are methods, and they are methods which are defined at the top level of the class hierarchy in Java, so they are valid for all objects. So here's an example of an account object. The account object has two public methods, deposit and withdraw, and we would like this to be treated as a monitor. By default, objects can be monitors, but are not necessarily monitors. If you don't put any critical sections in your class, then you get no monitor behavior. If, on the other hand, for every public method, you create a critical section, then you essentially have a monitor. So the monitor, the classical monitor, as it's known from the literature, all public operations are synchronized. So if you simply declare every public method to be synchronized, without having to say, use the synchronized block mechanism, but it's equivalent, it's just syntactic sugar, then you suddenly have a monitor. However, notice in this particular class, when we want to withdraw a certain amount of money, if that money is not available, if the assets are not there, then we can either raise an error, which is probably not a good idea, or instead we can wait until the money is there. So that means when a thread comes in that wants to withdraw this money, we can either return immediately and say, hey, this is an error, or we could say, oh, let's wait. We're expecting money coming in pretty fast, so let's just simply wait. So this is a programming decision which we'll discuss in more detail in the coming weeks. We'll see there are lots of ways of dealing with this question, but let's assume here that that's a reasonable thing we want to do. So here's a pattern, or rather an idiom within Java that you'll see over and over again. Here we have a synchronized method. We have a condition that is a guard for executing the method. We want the amount to actually be less than or equal to the assets. So if that is not the case, so if the amount is greater than the assets, we have a problem. So we should wait. And we loop here. Notice that this is not a busy wait, because we are actually making the thread not runnable, and we will wait until we're woken up by a notification from another thread. So this is not busy waiting, this is actual monitor behavior. So this is the classical idiom. We have a synchronized method, we have a condition, a guard. If the guard is false, then we wait. And by the way, in this wait should always be embedded in a try-catch clause, where you may do something in case you get an interrupted exception. More about that later, but it's not terribly important for us here. This is something you have to deal with in practical programs, however. If you get woken up from this, typically you'll want to check again if now the guard is true, because there may be multiple reasons why you get woken up from the wait. You don't know why you're woken up from the wait. So it might be that the condition is now true. Suppose some amount was deposited in the account, but it wasn't enough to change this condition. So you better check again. So some money came in, but it's not enough. You check again, maybe wait again. Eventually you'll get woken up and there's enough money. Now you can deduct the amount from the account and continue executing. And actually the method is over there. When do you get woken up? Well, this is very simple. There's some other method which is also synchronized. It's also must be in a critical section. In this case, it's deposit. And this method has no guard because you can always deposit something new. So there's no guard here. So there's no wait while. We simply increase the assets, and we know, because we're implementing the logic of this class, we know that if this happens, it may be that there's some other method which is waiting for us in its critical section. So we're going to just notify all threads that are waiting on this object. Not all threads in the system that are not runnable, only the ones that are waiting on this guy. So if there's anybody stuck in any thread stuck in a withdraw on this particular account, it will get woken up. It'll check the condition again, possibly proceed, or possibly go back to sleep again. This is the basic pattern in one slide, and this is what we'll be doing over and over again. As we'll see, there are lots and lots of variants of this, lots of things that can go wrong, but the basic pattern, once you understand it, is very robust, and you can use it to build very robust concurrent programs. Here we see an example of the account being used in practice. So here we've got a couple of threads, and one thread is wants to withdraw money, another thread wants to deposit money. So this guy wants to withdraw 100 units, and it's stuck waiting here. And then we have another thread which is trying to deposit, and it deposits the 200 units, and then finally this thread is woken up and continue executing. So here's our account project. We have the deposit and withdraw. We also have an invariant. So this is the invariant we want to check. This is quite important. The invariant is that our assets should never be less than 0. So they should always be greater than or equal to 0. If the assets fall below 0, then we violated our invariant and there's a problem, there's a bug in our program. So normally in a sequential program, we could ensure the invariant quite easily. We would simply check whether there's enough money available and withdraw if there is. However, in a concurrent program, between the time that we check and the time that we withdraw, some other thread might come in. So there might be 2 withdrawers that both check and then withdraw, and then we violate our invariant. So what we do is we instead make the entire withdraw method a critical section, and also the entire deposit method. These are critical sections. And we put a guard in the withdraw method. That means that if the guard fails, then we give up control of the monitor and allow another thread in to attempt a withdrawal or to deposit. We also check our invariant to make sure that nothing went wrong, so that there wasn't an error in our synchronization. And with our account demo, we create our 2 competing threads and we run them. And we see here that everything runs fine and we get no invariant errors. In classical monitors, wait and signal are keywords. In Java, interestingly, they're not keywords, but they're methods. And you'll find them defined in the root of the class hierarchy, the class object. This is because any object can potentially be a monitor. Notice that it only will be a monitor if you make use of critical sections, synchronized blocks or synchronized methods. Otherwise, wait and notify don't make any sense and can't even be used. Reasoning about concurrent programs can be very complex and difficult because there are many, many possible interleavings, many possible ways in which different threads can interact. What we're going to do is we're going to look at a very nice formal framework that abstracts away from the nitty-gritty details of our programs and thinks of these programs as finite state processes. That is, a finite number of interesting states that we would like to reason about. And this framework will, by what is known as model checking, allow us to check that certain undesirable states cannot be reached. We'll be using this throughout the entire course, and we'll have a very brief introduction to some very simple examples today. First of all, in concurrent programs, we have to deal with a certain amount of non-determinism. In particular, we have multiple threads which are managed and rotated, if you like, by the scheduler. Threads may be interrupted at any time. So they may be interrupted by the scheduler, they may be interrupted themselves because of I/O, or all sorts of things can happen. And there may be just timing differences between threads. So it's not guaranteed that any 2 runs will be the same. That can be a desirable feature or an undesirable feature of programs. It's completely open. So because the concurrent systems are non-deterministic, it can be difficult to build them and reason about the properties. So what we're going to do is we're going to model concurrency by abstracting away from this very detailed world and focus instead on the particular points of interest. So this is what modeling is. Instead of looking at all of the real world in all of its detail, we just highlight the points that are of interest. This is exactly what we'll do with our concurrent programs. We'll try and identify the particular states of interest and view a concurrent system as a set of threads which are sequential finite state processes. FSP stands for finite state processes, and it's a text-based notation, like a very simple programming language or domain-specific language for specifying a finite state process. Here, for example, we specify the process called switch, and it takes a bunch of actions. So we have processes and actions. A process can also stand for a particular state of a process. So switch is the process that allows us to perform the action on and then the action off, and then we repeat with the process switch. LTS is a graphical notation, and it stands for Label Transition Systems, which allows us to look at FSP processes, finite state processes, as a label transition system. Here we see the process switch displayed as such a finite state process, essentially a kind of a state machine with two states. So the state 0 is the state also known as switch, and the state 1 is the unnamed state, which we reach by performing a single on action. So this unnamed state is also known as off arrow switch. So if we gave this a name, we could define switched on equal to off arrow switch would be perfectly fine description of that state as a process. So we're basically switching between these two states back and forth. Now, what's the meaning of such a process? The semantics. Essentially, we want to think of a process as being a trace, so that is a sequence of actions that can be performed until it stops. So it may be either a finite string or an infinite string, a sequence of actions. But actually, processes may themselves be concurrent or non-deterministic, so you don't get just one trace, but a set of possible traces. In this particular example, there's only one possible trace, the infinite one consisting of off, on, infinitely. Here we see the LTS analyzer, or LTSA. This is a tool that's being developed in Java to interpret FSP programs and to display them as label transition systems. We can either write our FSP programs directly here, or we can open up existing ones. Here's a version of the switch program, which is defined as follows. Here, instead of directly writing switch as on arrow, off arrow, switch, we define switch to be the off state. So that's our initial state. The off state is equal to on arrow on. So if we have the action on performed, then we will go to the on state, and the on state will allow us to perform the off action and return to the off state, which is the same as switch. We can compile this, so there are a bunch of buttons here. So the compile will evaluate this, and now we can switch to the draw tab, which will show us all of the processes that were contained in this program. There was only one, which is switch. And we have some tools that allow us to explore the resulting label transition system. Notice the process that we defined was called switch at the highest level. So the substates off and on don't appear directly. The LTSA just generates states which are numbered from 0 up to n for as many states as it can handle. And here we can see quite clearly that this textual description, this one here, will generate this nice diagram. There are some various tools that we'll see throughout this course, but let's start with the simplest one, which is the animator. Here's an animator that tells us, well, in this particular state, there are multiple actions that are available in the system, namely on and off, but in this particular state, the only one that you're allowed to perform is on. So we can make a choice, but there's a choice of one. So we can start in this red state and then move on to state 1. So now we've performed that action, and now we're in the state 1, which is the on state. In this state, there again is only one action we can perform. We take it, and we're back in our initial state. We could continue doing this, but this is clearly it doesn't get more interesting than this at this stage. Now, there's more to FSP than we've seen here. We'll see a little bit more of the syntax in the rest of this lecture. Just for reference, here's a single slide showing pretty much all of the syntax of FSP, and we'll be using most of these features at some point throughout the course. But don't worry about them now. We're only going to look at a few of these features today. Most of them are pretty straightforward. They look rather cryptic, but there's not much to them. We'll explain them as we'll encounter them. Here's another example. This example is called one-shot, and it is showing again the action and prefix syntax, so the arrow syntax. So on the left-hand side of the arrow is an action, and on the right-hand side is a process or a process expression. We've seen that before in the previous example. What's new here is the special process stop, which does nothing. So one shot will allow us to perform the action once, exactly once, and then it stops. This is a terminating process. Notice that processes start with uppercases and actions with lowercase. So it's very easy to tell if you're confused by the syntax at some point what's an action and what's a process. And notice that a process and a state are pretty much the same thing. So from any state you could start, and there would be a new process state starting from that point. So here, for example, one shot, we start in this particular state. Once we follow that, we get to the state 1, which is also corresponds to a process, in this case, the stop process. We can load this example in LTSA and compile it, and we can show it. Here it is. It's not terribly exciting, and we can also animate it. Again, there's only one action available to us. We can perform it, and once we've done it, there's nothing else that we can do. So this simulator, the animator, shows us quite clearly that our expectations are fulfilled. Nothing else is happening here. We've already seen recursion. Here's the example that we saw in LTSA, so the alternative definition of switch. So switch is, here we have a definition which is composed of various parts separated by commas and ending with a period. So switch is equal to the off process. The off process is on arrow on, and the on process is off arrow off. So this is clearly a complete recursive specification. Here's a new feature, which is choice. So now things start to become a little bit more interesting. If we have actions X and Y, and both actions are possible at the same time, then we can specify that with an OR bar. Here, for example, we have a process in around parentheses that can perform either an X action or a Y action. If it performs the X action, it will become the process P. If it performs the Y action, it'll become the process Q, where P and Q, of course, also correspond to states in the overall process. Here's a concrete example, the drinks machine. So the drinks machine will allow us either to press a red button, at which point we can take a coffee from the machine, and then the machine returns back to its initial state. In the initial state, in addition to the blue button, we could also press the red button, we can also press the blue button, and the blue button would give us a tea. Notice that once we press the red button, we must take the coffee before we can again press another button, either red or blue. Now, in the examples we saw before, the traces were fairly limited. We had the unlimited trace of on, off, on, off, on, off. And we also had the one-shot process that performed the action once. There was only a trace, again, with a single trace with the string once in it. Here we have multiple possible traces. The question is, for the discussion, what are the possible traces of drinks? So far, our programs have been completely deterministic. So we decide whether to press the red button or the blue button. There's no non-determinism. We can have a process that is internally non-deterministic. When we take an action, we don't know what state it will go into. So here's an example of that, and it's kind of cool. So here's the pattern. We have a process, and it's a choice, but multiple choices have the same action. So the same action X might lead to the process P or might lead to the process Q. We from outside don't decide. It's the process itself that decides. As a concrete example, here we have a coin. If we toss the coin, it might come up heads or it might come up tails. And we don't decide. With the drinks machine, we decided whether to press the red button or the blue button, and then we got our coffee or our tea. In this particular case, we just toss the coin and we don't know how it will come up. Here's the coin cost program. We can compile it, display it, and we can animate it. So initially we have one thing that's possible, which is toss, and it just decided to go to state 2. It could have gone to state 1. Now it's heads. Well, we accept it. We look at the heads, and now we want to toss the coin again. So we can do that. We toss it again, and this time it comes up heads again. Do it again. This time it comes up tails. And it's completely arbitrary. It really depends on what the LTA system, the animator, have decided to do. We've seen in our Java programs that we have guarded actions. Now, how can we model the guarded actions in FSP? It's a little bit of a trick, and the trick depends on a kind of macro expansion. Now, let's see how this is working. Here's our FSP program. We start by defining a process count. Actually, there are multiple processes called count, going from 0 up to 3. So there are actually 4 of them. Remember the duality between processes and states. Every process corresponds to a state. Every state corresponds to a process if you start from that state. So here we're defining as kind of a macro 4 different count processes labeled I from 0 up to n. Notice this is still one definition because there's a comma here. The period is only at the end. So first of all, we define count for n is equal to 3. And this is the amount that we can count up to. And initially, we're going to start in the state count 0. So what are the different counts? Well, count 0 up to count 3 allow us to form an increment or decrement. There's this when clause here, and this is macro expanded. So basically, the idea is we'll instantiate count for every value from 0 up to 3, and the part that appears after the when will be there or not if this condition is fulfilled. So in the case that I is less than n, then we'll have the possibility of performing the action inc to count with the higher value of I. And in all cases where I is greater than 0, we can perform a dec action, and we will decrement and go down to the state count where I is 1 less. We could, of course, have written all of these processes out by hand, count 0 up to count 3, but that would be rather repetitive and boring. So particularly if we had more than 3 states, we had 100 states, this would just not scale. So this is a much more compact way of writing these boilerplate processes, which are all pretty much similar. So notice the initial one, count 0, only has an inc action. The dec action disappears because I is equal to 0. In count 1, however, we can either do an inc to count 2 or a dec to count 0. All the way up until the top, once we get to count 3 can only do a dec because this part disappears since I is no longer less than 3. Here's our count FSP program. As before, we can compile it, and then we can draw it. Here it is. And we can also simulate it. Notice initially we can only perform an inc action. Then we have a choice between incrementing and decrementing. So we can just arbitrarily move between any of these states by selecting the sequences. Question again is, this is one possible trace up to a certain point. What are all possible traces that we can reasonably reach with this finite state process? Think back to our competitors, the tortoise and the hare. Each competitor can take a series of actions in this race. So it runs a kilometer and then runs another kilometer up to a certain number of kilometers. In this particular case, a competitor is running 4 kilometers until it is done. We can model this in the same way as we did the previous example. We define a constant, n is 4, and the competitor runs a certain number of kilometers. The kilometers, if if the parameter is less than the total length of the track, then we can perform an action n for the next kilometer to be performed, and then go to the next state. At the end, however, we can only perform the done action, and then we reach the stop state. Notice that in this particular case, with our macro expansion, the when clauses will select either this action or that action, but never both, because these when clauses are mutually exclusive. Now, the interesting question is the following. We have two competitors, the tortoise and the hare, and we want to compose them together. So up until now, we've had non-determinism, but we had no concurrency. And this is where things get interesting. We have two finite state processes, and we want to compose them together. So we want the tortoise and the hare. So here's a trick, a little bit more syntax, which is relabeling. We take competitor and we prefix all its actions by tortoise. So now we've turned one of these competitors into a tortoise. So here's the tortoise competitor. It performs tortoise 1, then tortoise 3, and then tortoise 4, until finally it's done. Here we relabel, we have a new instance of competitor, and it's prefixed by hare. So it's exactly the same, except has a different prefix. So these are two separate finite state processes. Now with this operator, which is not the single OR bar, which is for choice, but it's a parallel two OR bars, and it says compose these two finite state processes together. Now what are you going to get? Now you get a concurrent system. But the way of thinking of this, composing finite state processes just creates another finite state process. What kind of finite state process do you get? And in the end, how many possible traces do you get, and how many possible states do you get? If we look at the composition, so here we have the tortoise and the hare. We can compile this, which is fine. Here we have the tortoise, here we have the hare. But what we really want to do now is we want to compose them together. So there's another operator here, which is this guy. So we don't just want to compile them, we want to compile them and compose them. And we get a little bit of feedback here, but we'll learn more about that later. Here's the tortoise and our hare, and here's the race, which is the two composed together. Well, this looks pretty scary. Notice there's a big mess going on here. We get all possible combinations. So essentially we're getting the tortoise and the hare being interleaved. How do we want to think about this? What's actually going on? It looks very complicated, but it's just a question of the way that LTSA is displaying this composition. I'd like to show you now that there's a very different way of thinking about it, which is much, much simpler, and it explains why we get these different states. In particular, why we get the precise number of states that we see here. Let's simplify the problem and consider the tortoise and the hare, each running a race of just 1 kilometer. So they'll each just have 3 states. If we compose these guys in LTSA, we get this diagram. That doesn't really explain. We get states 0 up to 8, and before we had states 0 up to 35. Now, you may have noticed something there, but let's think about what's going on. We have 2 processes which are running independently without any interaction between them. In other words, we have 2 processes, each with their own states, and we have all possible combinations of them. In other words, we can consider this as a new finite state process, which is the cross product of the original one. So now we get a new state machine where each state corresponds of 2 parts, one which is the part of the hare and the other which is the part of the tortoise. And here I've labeled them as such. Instead of having 0 up to 8, now we can see quite clearly we have the tortoise being 0, 1, or 2, and the hare being 0, 1, or 2 on the right-hand side. And now it's obvious. It's very clear. Each process had 3 states, and the composition of them has 9 states. Now, in this particular case, neither the tortoise nor the hare, they don't communicate with each other, and there are no restrictions between the possible interleavings. So we actually do get all possible states. As we'll see, however, that's not always going to be the case. In particular, if we get some interactions between these processes, then we'll get much fewer states. But that's for another time. So this explains how, in this case, the states 0 to 8 are actually 9 states, and the states 0 to 35 is actually 36, or 6 times 6 states. So there's nothing surprising there at all. And the way we generate this diagram, what LTSA did for us, as we can see here, it's just displayed in a way that doesn't show us what's going on, but if we rearrange all of these states into a nice square, it would become immediately clear exactly what's going on in this funny diagram. Let's go back to the state machine that we use to describe the possible states of threads in Java. Recall, we create a new thread. It doesn't become runnable until we start it. Once it's runnable, it can yield and stay in a runnable state, or it can sleep, wait, or do an I/O block to become not runnable, or wake up from the state when the time has elapsed, a notify is received, or the I/O is unblocked. And then finally, when the run method ends by itself or exits for some reason or returns, then we reach the final state. So there are 4 states of interest. We can model this very nicely with FSP. What's a thread? Notice this is one definition for thread, starting here and ending here with the period. And it consists of 3 parts. There's the thread part, which can start and become a runnable. A runnable can do a yield, stay runnable, sleep, wait, or block OI, become not runnable. And not runnable can awake, notify, or unblock to become runnable again. And from runnable, we can have a stop action and become the stop process. And this is exactly the behavior of our Java processes. And we can see it very nicely here in this diagram. That's it for today. We'll meet again in the discussion session and dive into some of these questions that were raised and a bunch of other questions in more detail. See you then.